Right now, at this exact millisecond, you are performing an absolute miracle.
Oh, definitely. A completely invisible one, too.
Right. Because, I am vibrating my vocal cords, pushing air into a microphone, which is converting those acoustic waves into digital data.
And then that data is streaming into your device, turning back into sound waves and hitting your eardrum.
Exactly. Sending all these electrical signals into your brain. And somehow, out of all that physics and biology, you are extracting meaning.
Yeah, you're hearing these words, interpreting them, and probably forming some sort of opinion about them right now.
And it is entirely seamless to you. You don't feel the neurons firing or the synapses bridging. It just happens.
We are completely blind to our own mental machinery, which is wild to think about.
And that mind-bending reality is exactly what today's deep dive is all about. We are taking a really comprehensive look at a Wikipedia article on cognition to decode that invisible machinery humming inside your head.
Right. Because the mission here isn't just to, rattle off some dry textbook definition of a scientific term.
No, we want to cut through all that heavy academic jargon and look at the actual mechanisms, the how and the why. We really want to give you a true understanding of your own mind.
We want you to be able to catch your brain in the act of thinking.
Which is a pretty profound goal,
Yeah.
especially considering humanity has spent thousands of years trying to figure out how to study something we literally cannot see.
Yeah, it's a huge challenge. But to start, we really should lay down a foundational baseline from the text.
Let's do it.
So the word cognition comes from the Latin root cognoscere, which literally means to know or to learn. So broadly speaking, cognition encompasses all the mental processes that deal with knowledge and information.
So it's essentially like the entire life cycle of data inside your head.
Precisely. It involves acquiring information from the outside world, transforming it into something usable, storing it, and retrieving it when you need it.
Like pulling a file from a hard drive.
Exactly. And ultimately applying it to interact with your environment. So when you're reading an article or learning some complex new software at work, or even just trying to remember where you left your keys, you are engaging in cognition.
But wait, if cognition is strictly about, knowledge and information and data processing, where do my messy emotions fit into this?
Oh, that's a great question.
Like if I get a sudden spike of panic right before public speaking or a rush of joy when I see my family, is that cognition? Or is cognition just the cold, hard, logical stuff?
That is actually a massive debate in psychology right now. And according to the sources, there isn't really a universally agreed upon answer.
Oh, really? I would have thought they had that sorted out by now.
Not at all. So on one side, you have these hardline cognitivists, and their view is that essentially all mental phenomena, even raw feelings, are cognitions.
Wait, how does that work?
Well, they argue that an emotion like fear doesn't just, spontaneously generate from nothing. It requires an underlying cognitive evaluation.
Meaning my brain has to do the math on a threat before my body can react with panic.
Exactly. You have to process the visual data of, say, a snarling dog, retrieve memories associated with danger, and project a future outcome of getting bitten.
And all that happens in a fraction of a second.
Right. All of that happens instantly to trigger the physiological state of fear. So to a cognitivist, emotion is really just the physical output of a high-speed cognitive calculation.
Okay, I see the logic there, but it also feels slightly reductive. Like a sudden wave of panic just fundamentally doesn't feel like the same biological mechanism as calculating a math problem.
And that exact skepticism is why many researchers draw a strict line between cognition, which they define as abstract reasoning, memory, perception, and raw affect, which covers feelings and emotions.
So they treat them as completely different systems.
Yeah. They argue those are two separate parallel systems that interact, sure, but operate on entirely different biological architectures.
Okay, it makes sense to view them as two distinct operating systems. But before we can get to the grand theories of how the whole brain works as an integrated unit, we really need to look at the individual stations on the mind's assembly line.
Right, like how does raw data from the outside world actually transform into a coherent thought?
Exactly. And according to the text, it all starts with perception and attention.
Yeah, perception is the first major station. It's the process of organizing and interpreting sensory information. We mentioned the sound waves hitting your eardrum earlier.
Or light bouncing off objects and hitting your retinas.
Exactly. These physical stimuli are detected by receptors and transmitted to the brain as raw electrical signals.
But the brain doesn't just hand you a spreadsheet of raw sensory data, right? It hands you a finished product. It gives you this seamless, high-definition experience. How is it doing that translation so incredibly quickly?
Honestly, It does it by cheating.
Cheat.
Well, to be more scientific about it, by using heuristics. The brain is highly efficient, processing every single pixel of reality, every fluctuation in light, from scratch every millisecond. That would take an astronomical amount of biological energy.
Your brain would literally overheat.
It would. So to conserve energy, cognitive processes rely on these heuristics. They're basically mental shortcuts to reduce cognitive labor.
Size constancy is a really great way to visualize this shortcut in action. Like if you see a car driving away from you down a long road, the actual physical image hitting your retina is shrinking, right?
Yep, getting smaller and smaller.
But from the perspective of pure data, you don't perceive the car as physically deflating like a balloon.
Right, because your brain uses a heuristic.
Yeah.
It assumes the physical properties of objects remain constant, so it automatically interprets that shrinking sensory data as the object increasing its distance from you.
So it just overrides the raw data with a pre-programmed rule about how the physical world works.
Exactly. It saves so much time.
But the brain is doing all of this automated processing while being bombarded by millions of stimuli at once. I mean, the feeling of your socks on your feet, the hum of the refrigerator, a text message popping up.
Right. If the brain tried to apply heuristics to every single piece of data hitting your nervous system, it would still crash.
Which brings us to the next vital station on the assembly line, which is attention. Attention is the filtering mechanism.
Yes, it prioritizes specific aspects of the environment while actively suppressing irrelevant information.
I kind of picture this like a really busy nightclub. Perception is the chaotic crowd of people outside on the street, all the sights, the sounds, the smells trying to get in.
I like this, okay.
But attention is the bouncer standing at the velvet rope. The bouncer strictly prioritizes who gets in. It's like, you, the important email, come in, you, the humming refrigerator, stay out.
And to take that nightclub analogy a step further, the bouncer isn't just passively letting people in based on a guest list. That bouncer is actively shoving people away.
Wow, really?
Yeah, it's a mechanism called cognitive inhibition. Your brain is actually expending metabolic energy to actively suppress the sound of that refrigerator so that it doesn't interrupt your focus on the email.
So it's an active blockade, not just a passive filter.
Precisely.
But there's a serious flaw in the bouncer system, isn't there? Because these heuristics, these evolutionary shortcuts the brain takes to manage the crowd, they can be hijacked. And that's basically all an optical illusion is, right?
Oh, completely. Optical illusions aren't a glitch in your physical eyes. They're a glitch in your cognitive heuristics.
The bouncer lets the wrong person into the club because they were wearing a really convincing disguise.
That's exactly it. Our brain's shortcuts are optimized for the natural world. So when we encounter artificial patterns that are specifically designed to exploit those shortcuts, the brain misinterprets the data.
Like bending straight lines into curves.
Right, because it's trying to force a 2D image into a 3D spatial heuristic.
Okay, so the bouncer lets the information into the club. We've perceived it, we're attending to it. How do we actually think about it? Because we have to organize it somehow.
We do that through categorization. So once information is in, we use concepts to sort reality into manageable buckets. But the source points out we really have to distinguish between two very different types of concepts.
Logical concepts and natural concepts.
Exactly. Logical concepts are rigid. They're defined by strict, unbending rules.
Like in mathematics or coding. You know, a triangle is a polygon with 3 edges and 3 vertices, period. If it has 4 edges, it is kicked out of the triangle bucket.
There is no such thing as a sort of triangle.
Right. But most of human reality doesn't really operate like a geometry textbook.
And that is where natural concepts do the heavy lifting. Natural concepts are based on fuzzy resemblance and utility without clear-cut boundaries.
Like the concept of a table.
Yeah, a standard dining table has 4 legs and a flat top. But a pedestal table with just one thick center column is obviously still a table.
Right, but let's push that. What if I move into a new apartment, I don't have any furniture yet, and I eat my dinner off a flattened cardboard box on the floor?
Okay.
Am I functionally categorizing that cardboard box as a table? Like, is my brain categorizing actual garbage as furniture?
In that exact moment.
Yeah.
Functionally, yes. Because natural concepts don't care about dictionary definitions. They care about utility and neural weighting.
Right.
Your brain recognizes that the cardboard box shares enough functional properties with a table. You know, it's flat, it elevates your food, you sit around it, that it crosses that fuzzy threshold into the table category.
That's wild. So once we have these concepts, both logical and natural, we begin to manipulate them, and that is reasoning. We are drawing inferences and solving problems by basically bouncing these concepts off each other.
And reasoning operates on a spectrum of certainty. The most rigorous end of that spectrum is deductive reasoning, which follows strict rules of logical inference.
So if the premises are true, the conclusion is mathematically guaranteed to be true.
Right, like a basic if-then statement in computer programming.
If a system is in a complete vacuum, gravity accelerates all objects equally. We are observing objects in a complete vacuum, therefore they will accelerate equally. It is a completely closed loop of absolute certainty.
But as you know, humans rarely operate in closed loops of absolute certainty. Most of our daily lives require navigating profound uncertainty.
And that relies on non-deductive reasoning, specifically, according to the article, a really common mechanism called abductive reasoning.
Yes.
Wait, I want to clarify the mechanics here, because when I hear non-deductive reasoning, my mind instantly jumps to inductive reasoning.
Which is very common.
Like observing 100 consecutive days of sunshine and concluding it will be sunny tomorrow. Inductive is about generalizing from patterns. How is abductive reasoning different?
That's a really great distinction. So inductive reasoning generalizes a broad rule from lots of specific observations. Abductive reasoning is entirely different. It's about finding the best possible explanation for a specific, isolated set of clues.
Oh, so it's essentially playing detective.
Exactly. Think about a systems administrator who sees a server crash, and the error logs show a specific spike in traffic, right, followed by a memory leak.
They can't strictly deduce what happened because a dozen different things could cause those exact symptoms.
Correct. But they use abductive reasoning to infer that, say, a malicious DDoS attack is the most rational, logical explanation that accounts for all the specific evidence.
So it's not a guarantee. I mean, it could theoretically be some bizarre internal software glitch happening at the exact moment a viral video drove traffic to the site.
Sure, but the attack is the best explanation.
Okay, so to summarize the assembly line. Perception brings the raw physical data in. Attention actively filters and suppresses the noise. Concepts organize the surviving data into fuzzy buckets. And reasoning lets us play detective to figure out what it all means.
That's the factory flow, yeah.
But this leads to the ultimate question. Who or what is actually running the factory?
And now we step into the realm of cognitive architecture. This is the blueprint of how all these components interact holistically.
Right, and for decades, cognitive science has been dominated by two massive rival theories attempting to explain this grand design.
The first one is classical computationalism.
And classical computationalism makes a very bold claim. It doesn't just say the mind is a metaphor for a computer. It argues that the mind literally is a computer.
That is the core premise. It posits that human cognition is fundamentally formal symbol manipulation.
Okay, unpack that.
Basically, it argues that your brain represents all information through internal strings of symbols, and it processes those strings using strict mechanical syntactic rules.
But wait, if it's just rule following, where does the meaning come from?
What do you mean?
Well, if my brain is just moving symbols around like a giant game of Tetris based on their shape, why do I actually understand what I'm saying right now? Like, a pocket calculator doesn't know what the number 3 means.
No, it doesn't.
It just has a mechanical rule that says input A plus input B triggers output C. Are you saying we are just biological calculators?
According to strict classical computationalism, yes. The theory suggests that human reasoning, planning, and language processing all happen at this fundamental structural level.
So the meaning doesn't matter to the machine.
Exactly. The syntax, the structure, and the rules drives the operation entirely independently of the semantics or the meaning of the symbols. The understanding you feel is basically just a byproduct of highly complex, flawless rule execution.
Man, that is tough to swallow. But there is a sub-theory within this camp that actually makes a lot of sense when you think about it. The language of thought hypothesis.
Oh, yes. Mental ease. Mental ease is a brilliant concept for solving a very specific problem in cognitive science. How would you explain it?
Well, the hypothesis suggests that before you ever think a thought in English or Spanish or Japanese, your brain is processing concepts using a built-in pre-linguistic internal code.
Right.
Mental ease is essentially the foundational operating system of your brain.
Exactly. And the mechanism of mental ease is necessary to explain how a baby, or even certain animals, can think before they have ever acquired a spoken language.
Right, because a pre-verbal toddler can clearly form a complex desire like, I want that toy on the shelf, but I am too short to reach it, so I need to cry to get an adult to hand it to me.
They don't have the English vocabulary to form that sentence, but they clearly have the complex thought.
Because, they're processing those beliefs and desires using this internal structural grammar of mentalese.
Their internal symbols combine into strings following strict syntactic rules, which generates the thought, which then drives the behavior.
It provides a really clean, structured explanation, but if you actually look at the biological hardware of a human brain, it doesn't look like a silicon microchip processing linear step-by-step code.
No, it doesn't.
It looks like a massive, chaotic, interconnected web of neurons.
Which is the exact criticism that birthed the massive rival theory to computationalism, which is connectionism.
Okay, let's talk about connectionism.
Connectionism argues that treating the brain like a linear computer is fundamentally flawed. Instead, it models the mind as a complex, decentralized network of interconnected nodes.
So it completely throws out the idea of central step-by-step processing.
Yes, it replaces it with parallel processing.
Let's visualize how information moves through this web, because it's not random, right?
It's highly structured, but in layers. So you have the input layer, which receives the raw sensory data from the world.
Right.
That layer sends signals deeper into the web to hidden intermediary layers where the actual computation happens. And those hidden layers eventually fire signals to an output layer, which dictates your final thought or action.
So if classical computationalism is like a single master chef in a kitchen strictly following a highly complex, rigid, step-by-step recipe to bake a cake,
Right.
connectionism is more like a massive jazz band.
Oh, I like that. Let's expand on that jazz band. The crucial detail of connectionism is that in this jazz band, there is absolutely no conductor.
So there's no master chef. There's no central boss neuron telling the other neurons what the final thought should be.
Exactly. So how does the music actually get made?
Well, every single individual musician, every node is incredibly simple, right?
Yes. They don't know the whole song. They are only listening to the volume of the specific musicians directly next to them.
And if the signal they receive crosses a certain threshold, they play their note. And if it doesn't, they just stay quiet.
And through a process of shifting the weights or the importance of these connections over time, which, by the way, is how learning occurs, the nodes fine-tune their responses.
And the song, the complex human thought, just spontaneously emerges from thousands of simple nodes playing their individual parts in parallel.
That is the magic of emergence. Complex intelligence arises from the decentralized interaction of simple parts.
And if this layered, weighted network of nodes sounds familiar to anyone listening, it's because this is the exact architecture underlying modern artificial intelligence.
Oh, 100%. The neural networks powering the AI revolution today, the large language models, the image generators, they are direct mathematical descendants of the connectionist models of human cognition.
We are literally building our most advanced technology in the image of our own biological jazz band.
It's pretty amazing.
But it's wild to think about the history here, because listening to us debate the nuances of syntactic symbol manipulation versus parallel neural emergence, it makes it sound like we've always had this incredibly sophisticated grasp on the mind.
We most certainly have not. Studying cognition is uniquely frustrating because you're trying to measure something that is fundamentally invisible.
Right. A cardiologist can dissect a heart and watch the valves pump. A neurologist can look at the physical tissue of a brain.
But you cannot put a thought under a microscope.
So how did we actually get from ancient philosophers guessing about the soul to building AI neural networks? It obviously wasn't a straight line.
No, it was a very bumpy ride. You had ancient philosophers like Aristotle trying to map it out. Later, you had Enlightenment thinkers like John Locke proposing the blank slate theory,
arguing that the mind has no built-in rules and learns everything purely through sensory experience.
Exactly. But the most massive roadblock in the history of cognitive science happened in the early 20th century with the rise of behaviorism.
Led by figures like John D. Watson and B.F. Skinner. And their logic, while incredibly frustrating in hindsight, kind of makes strict methodological sense.
Their argument was that science requires observable, objective, measurable data.
Which is fair.
Sure. But since internal mental states, thoughts, feelings, heuristics, mentalese are strictly unobservable, they argued that science should completely ignore them.
Wow.
Radical behaviorists decreed that psychology should only study what can be seen, the external stimulus that goes into an organism, and the observable behavioral response that comes out. The mind itself was deemed a black box that shouldn't be touched.
That is like trying to understand how a car engine works by only looking at the driver, pushing the gas pedal down, and watching the tires spin, but flat out refusing to ever pop the hood.
It's worse than that. Behaviorists didn't just refuse to open the hood. They essentially welded the hood shut and claimed that whatever was inside the engine block was irrelevant to the science of motion.
Just map the inputs and the outputs, and you've solved psychology.
Pretty much.
But eventually, that approach had to hit a massive wall. You cannot explain complex human behavior, especially things like language acquisition or creative problem solving, just by mapping inputs and outputs. You have to cut the weld. You have to open the hood.
And that profound frustration is exactly what sparked the cognitive revolution in the 1950s. It was a massive paradigm shift.
And crucially, it didn't just come from psychologists. It required an interdisciplinary rebellion.
Yes, you had pioneers in the brand new field of computer science, like Alan Newell and Herbert Simon, proving that machines could simulate human problem solving.
Showing that you actually could model invisible processes.
Exactly.
Yeah.
And concurrently, you had linguists like Noam Chomsky completely dismantling the behaviorist view of language.
Because Chomsky proved that children generate entirely novel sentences they have never heard before.
Right. And that is impossible under strict stimulus and response conditioning. It proved the existence of internal, universal generative grammar. It proved the existence of the machinery.
That realization birthed modern cognitive science, a true mashup of psychology, neuroscience, linguistics, and artificial intelligence.
And decades later, the invention of fMRI and brain imaging technologies finally gave them the flashlight they needed to look inside the black box.
They could finally see which physical regions of the biological hardware lit up when the abstract software of the mind was running a specific task.
It finally bridged the gap between the physical brain and the abstract mind.
So what does this massive journey mean for you, the person listening right now? It means that you are currently operating a machine of unfathomable, staggering complexity.
Every single day.
Every time you navigate a new city or read the room to see if your joke landed or evaluate a moral dilemma, you aren't just doing it. A miraculous, invisible collaboration is firing off in milliseconds.
Evolutionary heuristics are filtering out the sensory noise.
Natural concepts are categorizing the chaos. Weighted neural networks are playing their parallel jazz band song to present you with a finished, polished thought. You are now equipped to notice the mechanics of your own existence.
And as you go forward noticing those mechanics, I want to leave you with one final, deeply provocative concept from the sources regarding how your brain actually interfaces with reality.
Oh, I'm ready.
We talked earlier about how the brain uses shortcuts to save energy. Well, the ultimate energy-saving theory in modern cognitive science is called predictive coding, or Bayesianism.
Where the brain predicts outcomes to handle uncertainty, but what is the actual mechanism there?
The mechanism is called prediction error. Processing raw sensory data from scratch takes a relatively long time biologically. By the time your brain processes the visual data of, say, a baseball flying at your face, it would already have hit you.
So your brain doesn't passively wait for data?
No. It actively hallucinates the immediate future. It projects its own internal model onto the world.
Wait, it hallucinates reality before it happens?
Yes. Your brain predicts what you are about to see, hear, and feel. And the raw sensory data coming from your eyes and ears is only used to check the brain's math.
That is insane.
The only information that actually gets processed up the chain is the prediction error, basically the sensory data that contradicts your brain's hallucination. If the world matches the prediction, your brain just lets you experience the hallucination because it's computationally cheaper.
So wait, what does that imply about my experience of this exact moment?
Well, it raises a profound question about existence. Are you ever truly experiencing reality as it objectively happens? Or are you just constantly living inside your brain's best guess of what the world is about to do next, only occasionally being corrected by reality when your brain gets it wrong?
Wow.
Yeah. As you hear the final words of this sentence, are you actually hearing my voice, or did your brain just predict the sound waves before they even hit your eardrum?
That is definitely something to chew on the next time you decide to trust your own senses.